first of all, thank you very much, everybody, for joining us for this webinar, and in particular for the three participants. We have here Dr. Giacomo Tarroni, Dr. Alex Ter-Sarkisov, and Dr. Carlos. Hi, Carlos. You have you interrupted me, but Reyes Aldasoro. Okay, and this is, as you know, a webinar with artificial intelligence and healthcare that is co-organized by the School of the Science and Technology of the City University of London and the Institute of Science and Engineering for Medicine. And we have also here as one of the organizers, Stephen O'Connor. Hi, Stephen. So this is going to be very simple. Each participant will have 15 minutes in the order I have just introduced them for the talk, and immediately after each talk, there will be 5 minutes for questions and answers. At this time, all you have to do is just to ask for, you tell us that you want to ask a question, and I give you the floor. You can also use the chat to ask questions as the speakers are giving their presentations. Otherwise, please keep your mics off, obviously, except the panelist who is presenting at the time, so that there are no noises in the background. And I think that is pretty much all I had to say. Please take into account that this event is being recorded as well. So you don't feel comfortable with that, you will have to leave. And without further ado, I would introduce first Giacomo, please.
Yeah. Hi, everyone. Let me just start the screen sharing. Okay. Right. Hopefully you can see my screen, correct?
Yes.
Okay. Eduardo, thank you for the introduction. Good morning, everybody. I see the numbers of the participants going up, which is very nice. Thanks a lot for joining us. And thanks a lot to the organizers for inviting me again to this new webinar on AI in healthcare. The title of my talk is Taking Hearts to Heart, and will be about an AI-based automated quality control for cardiac MR images. I will try not to focus too much on the actual technique itself, but more about the steps that were involved into implementing it and what could be the impact, the real impact in the clinical scenario. So very quickly about me, I currently hold a full-time position as lecturer in AI at City University of London, and I'm also honorary research fellow at Imperial College. I'm also a member of the CTI Research Center, of which actually Eduardo is the director, Alex is another member, and we do a lot of cool things. So I really suggest you to go and have a look at our website, as you can see here. Now, some of my research interests include unsupervised anomaly detection and segmentation for medical images, federated learning in healthcare, interpretable shape analysis, and last but definitely not least, quality control and motion correction for cardiac MR images. And this is what we'll focus on for this talk. Right, so let's imagine that you have to undergo a cardiac MR scan. So you wake up, you go to the hospital, you go through all of the preparation, and then at some point you're inside the actual scanner. In the room just adjacent to that, there's the operator, there's like sort of controlling the different scans. The first scan that he will acquire is called the transverse localizer image. Actually, by the way, the things that I will show you in this slide are a bit of like a simplification of how things work, but they're essentially what's going on. So the operator will acquire this very quick scan called the transverse localizer image. The only aim of this scan is to identify where your heart lies in your body and how it's orientated within it. Then it will select a perpendicular plane, which you can imagine going through the slide in front of you, and acquire a second image that's called long axis two-chamber view. And it's called two-chamber view because you can see both the left ventricle here, where the white part is where the blood is, and the somewhat like grayer area that's surrounding it is the muscle, but also the left atrium. Then it will select another perpendicular plane, and this way we'll acquire what is called long axis four-chamber view. Four-chamber because you can see both the left heart here and the right heart just next to it. Then it will select another perpendicular plane, And in this case, what you will acquire is the image at the top, which is a short axis slice. So here you can see the left ventricle as this sort of like circle, white circle, surrounded by the myocardium for the left ventricle. And next to it, you have the right ventricle. Then the operator will continue this procedure by acquiring more and more adjacent slices. So to essentially acquire a full stack of these different slices. Now, for a proper acquisition, the operator will need to, of course, dial in the position of the first plane to acquire, which is called apical plane. And it's called apical plane because it's going through the apex of the left ventricle. But it will also select what is the final plane to acquire, which is the basal plane for the basal slice, essentially, which is the one going through the mitral valve. So this valve here for the left ventricle. Now, these planes are manually selected, right? So it's the operator that, based on all of these images, decides where to start and when to stop. And another bit that it's important to remember is that essentially for each of these different short axis slices, you as the patient will have to hold your breath while the image is acquired. Now, what can go wrong during an acquisition like this? There's many things that can go wrong, but two of the most important issues are highlighted in this slide. The first one is about heart coverage. So for a proper scan, you would want the short axis stack that you see here superimposed to the long axis one to go all the way from the apex of the left ventricle to the mitral valve. But if the operator didn't do his job properly, you will have potentially a lack of coverage. So just a portion of the heart that is not being imaged. Another issue has to do with the interslice motion. So if you were able to hold your breath throughout the acquisition, always in the same spot, then you will end up with a nicely well-aligned stack of slices. If this was not the case, you would see what happens at the bottom, where all of the slices are essentially misaligned. And both of these issues can have a sizable impact on the subsequent clinical assessment that the radiologist would want to do with these images, which was the first reason for you to go to the hospital in the first place. So what is the current practice and its limitations for quality control of these images? Quality control for these short axis stacks is performed by the operator through visual inspection. So the same operator that is doing the acquisition will have a quick look at the images and decide if they're good or not. As you can easily guess, this is very time consuming and also highly subjective. It's also unfeasible in very large scale studies, like for instance, the UK Biobank, which is this huge data set of 100,000 subjects with full MR studies. In these studies, operators don't really have enough time to go through each of the acquisitions and check if all the images are correct. So this bears the question, can we automate this with AI? Well, if we want to do this, the first question that we need to ask ourselves is, what do we actually want to predict? The most straightforward to go about this would be essentially going through a classification task. So we could get a bunch of short axis stacks like these ones here, show them to a set of expert annotators, like radiologists usually, and ask them to label which ones are of good quality and which ones are not. Then with this annotated data set, we could train an AI model for classification. And this model would then be able to predict for each of the stacks if they are of good quality or not, with some certain degree of accuracy, of course. Now, this is fine and it can be done. However, we might be more interested in trying to estimate quantities related to these quality issues rather than just labels. So if we wanted to do something like this, we would still get the same set of images. We would still ask the help of our annotators, but we would ask them to be more precise in their annotations. So we would want them to tell us, okay, this stack has only 90% of coverage for the left ventricle. This one just 85%. This one has good coverage, but the slices 3 and 5 are misaligned. This sort of information. Now we could feed this annotated data set again to another AI model, AI algorithm, and then the model will be able to predict this sort of information as well. When I started to work on this in this topic, me and my colleagues at the time, we wanted to try to develop a model based on regression for quality control that would also be highly interpretable. So this is how we came up with this interpretable quality control pipeline. So what was the first step? The first step was data collection and annotations. So we took a bunch of scans from the UK Biobank, and we asked the annotators to go through them. You can see here that the scans were the different long axis views and the short axis stacks. And we specifically asked them, we asked the radiologists essentially, to first segment the left, oh, sorry, I don't see my mouse. To first select, segment the left ventricle cavity in all of these images, but also to identify landmarks in the long axis images. The landmarks being the apex here at the bottom of the left ventricle, and also the sort of like points around the mitral valve that you see here at the top. We asked them to do this for 500 scans, which is not too many for most modern computer vision models, but it's quite a lot if you imagine that radiologists have to sift through all of these scans and do these annotations. Once we had the dataset annotated, we could move to model training. Back then, we used an algorithm, well, a technique, I should say, called the hybrid random forest. And we trained a different model for each of the different modalities. These models were able to provide then as predictions at once probabilistic segmentation maps, that you see here in white, highlighting the left ventricular cavity, and also the positions of the landmarks. Now, once we add those, sorry, let me actually show you again. Well, with this information that you see here, so what our models were able to predict, we wanted to essentially leverage them to then perform two quality checks. So this is essentially all that we have to play with in order to identify if those two issues that I mentioned before are actually occurring. So the first one, the first check is about heart coverage estimation, which was performed through landmark detection. So we have our landmarks for the apex and mitral valve in the different images. We can then compute median landmarks, both for the apex and for the mitral valve, and you see both of them here. And then we can simply compare the position of the short axis stack to that of the two landmarks. And we can easily tell, for instance, that in this case here at the top, there's a bit of lack of coverage in the basal area because the ending point of the stack should have been here. And the same happens in the apex. So we can easily measure the difference between the two distances and say that in this case, there's only a 79% of coverage. Now, what about the second check? Motion detection was performed through segmentation map comparisons. So we have the long axis images and we have here the short axis stack. Thanks to our trained models, we have our segmentation maps, right? Then we can go, slice by slice in the short axis stack and compare the position of the left ventricle, that is like a circle in the segmentation maps for each of the short axis slice, to the essentially the intersection of the long axis views for that specific slice. So essentially we can compare the center of this circle here that you see in red with the center of this asterisk. And that gives us like an estimation in millimeters for the displacement between the correct position and where the slice was actually showing the left ventricle. We can also create these nice color maps that at a glance show us that, for instance, in this case, these two slices are quite misaligned with respect to the other ones, which are instead quite well aligned, again, with the long axis views as reference. And since we're here, we can also move one step further and do not just motion detection, but also motion correction. Because since we have measured those misalignments, we can just apply them as translation to each of the slices and perform motion correction. So in this case, you can see, sorry, the mouse here, you can see that in this stack, there's these two slices that are clearly misaligned. And by performing this correction step, you see that now all the slices are nicely aligned. Now, we coded all of this pipeline in Python and C++, and we trained it on an Intel CPU-powered workstation, so no GPU. Now, nowadays, if you want to implement this with deep learning, which is, of course, the way to go, you would need the GPU. But I thought it was nice to show a project in which we were able to actually implement a very useful tool with quite good accuracy without the need of GPU. So it's not necessarily always needed. We then measure the performance of our pipeline in many ways, and we got some very good sensitivity and specificity metrics for both of the tasks. Now, wrapping up, okay, we have this pipeline. What can we do with it? Well, we could use it for near real-time assessment during acquisition, because the quality control of one single scan using this pipeline requires only roughly 14 seconds. So we could envision to have this next to your operator and just have the tool run after the acquisition and say, well, yeah, the quality for these images is very good. Or say, look, you missed a bit of the left ventricle, ask the patient to stay a bit more and reacquire those images. But another application is retrospective assessment on large data sets. And that's exactly what we did. We ran this pipeline on the first 20,000 scans of the UK Biobank that I mentioned before. And we were able to actually come to some interesting conclusions. So in this plot, you see the heart coverage for the scans acquired at the first UK Biobank imaging facility, which was in Cheadle. Next to the one of the images acquired in Newcastle, which was a second facility. And you can see that the scans in Cheadle have a non-negligible amount of scans that have less than 100% of coverage, which is then suboptimal. And we actually showed this to the UK Biobank team, who was actually collaborating with us. And they could see that actually this is what was going on, and they were happy to see that the protocols that are in place in Newcastle were actually working better. So they also managed to improve the ones in Cheadle in the first place. Okay, so final slide. What are the perks of interpretable quality control for cardiac MRI? Well, first of all, it provides quantitative metrics that can be easily explained, because you can tell the radiologist, look, this is where the landmark is, you're missing a bit there, which is very helpful for them. It's very fast, and differently from the radiologist, doesn't get tired. It can also correct some issues, as you've seen for the motion correction bit. It can be used both during acquisitions, but also retrospectively on large data sets. And this is all great, but it also would require an in-depth and much longer validation to then be actually used in the clinic. So, you know, there's always some way to go for these tools to be then practically used in the end. That's all for me. Thanks a lot, everybody.
Okay, thank you so much, Giacomo. Very
thank you.
So anyone has any questions, you can type them in the, in the questions and answer, facility that you have at the bottom of your screen, I hope, bottom right. We have one from Bahadar. Okay, can you read it yourself, Giacomo?
Yeah, let me just fetch it. Can you comment on CMR images with low signal to noise? Very good question. So I just showed you the first two checks that we were running. I assume you're asking about what the tool can do. If that's the case, I just showed you the first two quality checks. There's actually a third that the pipeline does, which is on contrast, on image contrast. I didn't have time to also talk about that, unfortunately, but you can have a quick look at the paper if you're interested. Long story short, with the segmentation maps that we have for the left ventricular cavity and the left ventricular myocardium, that would be useless for the two checks that I showed you up until now. We can measure what is the difference in intensity with respect to the dynamic range of the image. So that gives us sort of like a proxy for how well the image is in terms of signal to noise ratio. When that difference is relatively low compared to the full dynamic range of the image, then it means that you cannot really tell the difference between the cavity and the muscle, and that's then not really a great scan in the first place. Second question, would it be possible to do the short axis slice automatically instead of checking afterwards whether they are correct? So you mean automatically planning for them? If that's what you're referring to, yes, it is possible. There are tools that do that, but as it happens often in this line of work, there's many potential tools, but in the end, most of the work is done manually by the operators. So the answer is yes, to an extent. Then there's a question from Vasilis. Hi, Vasilis. Has this stream of work been followed up with DNN-powered algorithms? Not that I know of. There are pipelines to do the segmentation and the landmark detection, of course, plenty of them. But we didn't follow up ourselves on implementing those for quality control. But that's something that you could do, and essentially would probably just see an increase in the overall performance. So another question from Alex, how we can be sure that the motion correction won't correct a real anatomical feature out of the image? Good question. The reference against which you perform the correction are actual long axis views of the heart that you have, that you're scanning. So if there's a real anatomical feature, it will be picked up from those images as well. And so the correction will just match that as well. I hope this answers it.
Okay, thank you very much, Giacomo. Thank you, everybody, for very interesting questions, obviously.
Yeah, thanks a lot.
We might actually have at the end of the session a couple of more minutes if you want to keep on, asking questions to the panelists afterwards. But I think that we are just, on time for the next talk by Alex. Alex, do you want to connect, please?
Hi, yes, Eduardo, can I get started?
Yes, sure, please.
Okay, so I will try to keep it as short as functional as I can, meaning I will skip a lot of essential details about deep learning, and I will try to focus on the application as well. So I'll go straight to the main finding. So two main things is
Sorry, Alex, are you sharing your screen?
Oh, yes, sorry. Apologies.
No problem.
Can you see all?
Yes.
Okay. So the main findings, the work I'm doing is analyzing the computer tomography scans and slices for coronavirus prediction. So there are two different problems we're dealing actually with. So first is a classification problem, and classification problem means that you have a large set of images, in this case scans, and you run them through some program, and the program classifies them as one of three classes in this case, which is coronavirus, common pneumonia, and negative, healthy. That is a classification problem. The other problem is detection and segmentation of lesions in chest CT scans. And segmentation means finding masks of lesions, which I will explain shortly. So these two problems are actually different, but there is methodology that I will talk about that manages actually to unify, to combine these two objectives into a unified network. So first, I'll go really quickly over what CT scans are. I'm pretty sure everyone's known that, but they are different to X-rays in two ways. So first of all, it's axial rather than frontal, and they are slower to interpret than X-rays. And one more thing that is really important to us is that analysis of CT scans for coronavirus is more accurate than just than X-rays, and faster than polymerase chain reaction. So here in this image, you see, so the one on the left is a corona-positive scan. It's a slice, it's not a full scan. The one in the middle is a common pneumonia, and the one on the right is a healthy one. Again, they may belong to one, at least like A and C. A and C or B and C can belong to the same person because of the specifics of these slices of chest CT scans. So I'm working with slices. So an important thing in order to distinguish between common pneumonia and coronavirus is that they have a lot of commonalities, a lot of overlaps, and the differences can be quite subtle. So for example, here you see that the lesions on the left are very similar, but the one that has coronavirus has another lesion on the right, unlike the common pneumonia. So these subtle differences, is the reason why, one of the reasons why we want to use deep learning. So I will give a really short explanation of deep learning is. So it's a methodology that allows solving a lot of interesting questions in computer vision, such as classifying images, detecting objects, segmenting objects. I'll explain it like in a minute what that means. So the way it works is that there is a sequence of things that we call blocks. And what they do, they extract things called features, and then they combine those features in a hierarchical manner by in a sequential way, in a hierarchical manner, starting with primitive features like geometric features and finishing with high-level semantic features. When you take all of that together, we're talking about a model architecture. So here you see what features are. So the reasons why we extract them is because they're relevant to a particular problem that we are solving. So here there are two, the problems we're solving with lesion detection is the image on the left. So detection is, roughly speaking, finding this like bounding box around an object, and segmentation is the one on the right, meaning for each object, for each lesion, we find a mask. So these colors are their masks for each object. So the mask would be the this area, the accurate area of the lesion. So these two problems altogether we call detection and instance segmentation. So how does it work? So the kind of models that deep learning models are called convolutional neural nets. So there's lots of them, open source, lots of data sets, all open source. So what can they do? What can they do for lesion detection and for COVID detection? So the only name that I will be using here is the state-of-the-art model called MaskR-CNN, which detects objects with bounding boxes and segments objects with masks. What is really important here is that the model understands objects at the instance level. So it does not confuse two objects of the same class, for example, two lesions adjacent to each other. And this is really important. So it understands images both at individual level, both in terms of its localization and its mask. So what we have here, so we have two setups here. So first setup is the problem we're solving. So we have three types of objects in each CT scan, which is two types of lesions, ground glass opacity consolidation, and clean lines. The rest is a background. So what we want to segment each lesion with a high accuracy. So a high accuracy means that it overlaps with some ground truth that we need. So what is that ground truth? So that we found open source 750 scans from COVID patients that are labeled. Each scan is labeled at pixel level, meaning we attach each pixel one of the three classes: ground glass opacity, consolidation, clean lungs, and the rest is the background. So what we're doing here, we are predicting each lesion separately. So this is what an image, and this is what the ground truth look like. So the one on the left is the actual scan. The one on the right is its mask. Black is background. Red is GGO. Blue is consolidation, and the rest are clean lungs. So this is what we need to train deep learning models, and this is the output. So I'm fully skipping all functionality here. So this is one of the scans that we tested. So this tested scan was not a subset, was not a part of scans that was used for training. This is a new one. So the one on the left is the detection and segmentation of a lesion present in the lung. So you see it's 0.99 is very high confidence. See very accurate mask, very accurate detection. The one on the right is the one I called ground truth, where the light green one is the actual lesion, and the one in the middle just a score map with some related to confidence. Now, there are like just a couple of more examples of what instance segmentation models do. So this is the same data set, except that we're only finding clean lungs. So we accurately find clean lungs on the model, finds them very accurately on the left, very confidently. And it accurately avoids, if you look at this area on the left bottom part of the left lung, it carefully avoids this lesion area. This is yet another example which I used in, so the previous one was computer tomography. This is X-rays. So this is another project I was doing. So as you see, the predictions of clean lungs, prediction of lungs in X-ray are also very accurate, are also very confident. If you look at the ground truth on the right and the modal prediction on the left. So now we're coming to the main idea that I would like to present. This is the stuff I'm working on now, is that we can combine two things. So I skipped the classification because I believe it is a reasonably straightforward idea, is that we take different types of images, run them through the model, and the model classifies them as one of the classes, which is coronavirus, common pneumonia, and normal. Okay, so these are two different problems, and what I'm presenting here is a unified network for those problems, meaning a model that solves both problems at the same time. So two things why it is good. So first of all, the big advantage is that, like you all know, we need a lot of data to train deep learning models. So the first advantage of this framework is that the demand for the data reduces very substantially. So I had a data set, there's a data set with 100,000 scans. I used only 1% of that data for training and the rest for testing. And at the same time, because at the same time we use this functionality that detects lesions, which combines to the ability of the model to learn. And this is why it's the first reason it's good. And we need two data sets now, the one previously for lesion detection, and then the one with the classification. So two things, so several things are really important here, is that there are two branches now in this model. The one branch that classifies, the other branch that segments lesions. And what happened, the kind of idea I got, is that these branches, they sort of exchange information between themselves. So segmentation branch forwards some information to classification branch and vice versa. As a result, why this is a good idea, I think, why this is a useful idea, is because it improves the accuracy. It improves the accuracy of both models on their respective problems. Second thing, as I mentioned, we only require a small fraction of the data to achieve these results. And we, as you probably all heard, these deep learning models are huge. They are huge, but the trade-off here, the reason why this framework is interesting, is that in order to achieve this high accuracy, we do not need to train the whole model, which can be even hundreds of millions or 50 million parameters, 50 million weights that we need to train. We can actually just train a fraction of the model, again, something like 10% of the total size, in order to achieve this high accuracy. So this is the architecture of the model. Obviously, I'll just say just a couple of things here. So the scans on the left are, one of them is for segmentation, the other one is for classification. Then we have this feature extractor that kind of extracts the features I mentioned earlier, useful information from them. And then there's purple and red rectangles, purple and red parallelepipeds. this is where the magic happens. This is the mode. This is the layers that both detect useful features for classification and useful features for segmentations. And above at the top, you see this the ground truth mask, as I explained earlier, that is used to train segmentation. And at the bottom right, at the far right, you see these labels that are used for training the classifier, meaning that a model that takes this input scan and classifies it as either coronavirus or common pneumonia or normal. So here you see the output of this model. So the scans in the middle are the ones that we already seen before. So these are the outputs of this model, of the segmentation branch of this model. And so the one on top is a coronavirus, and the one on the bottom is normal. As you see, the ground truth mark, there are no lesions. And the values on the right is a confidence about the class of the input image. So the input scan, whole scan, not any areas of that. And these values, if you take the largest value here, unfortunately, I should have really put it down. If you take the largest value in each scan, then you get the confidence of the model about the class. The one on top, the third value, 16.2, is the confidence about coronavirus. So it is correctly predicted. The one on the bottom is +0, 3.168. That is a normal one. So again, the confidence of predicting both the lesions and the classes of the image that uses this lesion detection information is very accurate. So I'm got some results here. If you're curious, have a look. They, roughly speaking, mean that we need to train only a small share of the model on a small share of the data in order to get high accuracy. So here are the accuracies. So the way we determine segmentation accuracy is by taking an overlaps between predicted area and the ground truth area. The way we find accuracy for the classifier is to take the share of true positives for each class, adjust them for the class size, and divide by the total number of observations. That will be table 3 at the bottom. So as you see, I didn't put down, because of the space, I didn't put down here the other literature results in the literature, in the community. But these results are quite good. They're very competitive. So what it is that I would like to do next is to apply these ideas in a real life environment, which would be probably a hospital. The reason that it's a challenging thing is because the acquisition of chest CT scans is very dependent on the equipment. Equipment varies from hospital to hospital. So it might be a very challenging idea to create one model and apply to absolutely any hospital. This is called generalization. So in general, deep learning models generalize really well to unseen data. That is not the case here, for the exact reason I just said, that the difference of CT scan technology that varies from hospital to hospital. But the application, the implementation of that deployment of this model in one particular hospital should be very successful because of the homogeneity of the scan and chest CT scan information acquired in that particular hospital. And in the next, if that is successful, if we switch to another hospital, then we can adjust, which is called transfer learning and fine-tuning that model to the new data. And then that would be success. That would be an accurate prediction in the other hospital. Now, the really important thing is why we want to do all that. So there are different reasons.
Alex, you need to start, because you have 4 questions. We need to.
Yeah. Okay. So there's just some recent publications on that. Now, why this is all good is interesting is because it can help medical practitioners save their time with true negatives, for example, and just essentially cut the costs and cut the time waste. That is it. Thank you. So there's data and GitHub code, the publications.
Thank you so much, Alex. Very, very interesting. You actually have 4 questions in the questions and answers. Can you go through them, please?
I'm just not sure. Are these questions for me?
Yeah, from Stephen Skett, then
okay.
and Virginia has asked 2 questions.
Yes, sorry, I should have scrolled all the way down. What is the minimum number of patients you would use for training a model? That is a very good question, because we do not need for the full scan, for the accurate prediction, we do not need the full scan. We can just take, I don't know, every 10th slide from, I can't tell you the exact number, but I can tell you, given the stuff I told about today, I can say if you have, for example, any number of patients, I would need probably about 10 to 15% of those patients in order to train and deploy the model, because of this because of this unified functionality of segmentation and classification. So yeah, I hope I answered that. What is the difference between validation and testing? So that is actually a really good question, because a validation, roughly speaking, a validation, so you train the model, right? Now, the thing is that you don't know which one of them is actually the best. That's why you need validation, meaning you take another subset of the data and you run the model on that data. And then if data says, well, no, you're overfitting, you've gone too far, then I scale back and find a better model, and then I use it to test the actual real data that we have unseen. So it's for this thing called overfitting, when we know when to stop the model training. Okay. How do you prevent classification bias affecting the segmentation branch, and vice versa? That is yet another good question. So I use that is dependent. That depends on the. So the way model trains is that we need derivatives. We need to find gradients derivatives for each weight, for each parameter in the model. So when they exchange information, what I came up with is we control the computation and the copying, the exchange of these derivatives. So for example, if I've seen far too many coronavirus, so the coronavirus accuracy defeats the accuracy of other classes. So I would reduce the gradient exchange for that kind of class, and so on. But this is a very interesting and deep question, and if you contact me, we can discuss it in greater depth. I think lung tumors, similar morphological characteristic of types. Do you have a way during your curation ensuring training do not lung cancer? That is also, yeah, I really appreciate great seminar, great questions. The thing is, your models are as good as your data. So if the data is bad, your models are bad. And the data I got is from open source, CNCB and COV. I highly recommend it. So it was labeled at mask level or image level by the specialists at that hospital. So if they messed up somewhere, if they confused these lung tumors with COVID, then that is an issue. But again, deep learning models are so strong and interesting and generalization wise, that we, under certain conditions, if we kind of work on that, probably at without the model, just analytically, we can find a way of the model to provide accurate predictions for coronavirus, ignoring unrelated positive cases such as lung tumors. So a long story short, a deep learning model can avoid this pitfall by the way of the setup of the training.
Okay.
I think there's
this one, the last one, we really need to proceed with Carlos.
Yeah.
The last one from Richard, you can actually type the answer.
Yeah, I'll just say ResNet, just ResNet, or just email me. We can discuss that. Thank you.
Thank you very much, Alex. Okay, Carlos, I think it's your turn now.
Thank you very much. Let me share my screen. Okay, so the last the talk is going to change the point of view, and this is literal because I'm going to go deeper into the resolution of what we can see in the human body. And both previous presentations were into the macroscopical part, so seeing all the things that we could see at the macroscopic level. So I'm going to go into the microscopic level, and it's looking inside the cells and looking more at details of the cells. And this is related to cancer. So we may be familiar with cancer that develops when a single cell has a problem in the DNA. There is a mutation in the DNA. And when the cell is able to subdivide, it can go and bypass many of the mechanisms that the body will have to prevent cancer from developing as tumors. And what I would like to highlight is that at the moment, about 1 in 6 of us will die of cancer. So 1 in 3 may die of a cardiovascular disease, which is still the biggest killer of them all. But 1 in 2 people are developing cancer. And that means that if 1 in 2 are developing and 1 in 6 are dying, there are many people who survive cancer. And we can survive cancer thanks to a lot of research. And here I would highlight the UK-based charity Cancer Research. And there are many parts in which the research that we are doing, we as collectively, all the scientists working in these areas, can improve that from 1 in 2 to 1 in 6. And there could be clinical drugs and different things. But one of the basic things is cancer biology, understanding the basic nature of the cancer cells. So what does that mean? That we can see cells and they can be a certain type. So if we have healthy cells, they can have a certain shape and a certain color and certain conditions and texture and other things. And then cancer cells are different. So they can have mutations that manifest as in different textures or having more than one nucleus or changes into the physiognomy. And this is what I'm going to be looking at today. And this is starting from some particular type of cells that come from a patient called Henrietta Lacks, which in 1961 developed a cancer, and she went to hospital. And upon examination, she had a malignant tumor. And unknown to her, and without her consent, they took some cells of this tumor and they were sending to a lab. And that was common practice at the time. So it was not necessary to give consent, which is totally unethical, of course. And then she died. Sadly, she died. However, her cells follow a very different path. And there is now a book and a film called The Immortal Life of Henrietta Lacks, because these cells didn't die. And at that time, it was not possible to keep cells alive in labs. And her cells started doubling every 24 hours. So it was a very, very aggressive tumor. And those cells are still alive today. And they're used in every kind of experiment. There are people who made calculations of how many cells exist. And if you put them one next to the other, you can go from the Earth to the moon and then come back. So you can imagine how many cells are there. And these all come from a single tumor, from a single person. So these are called HeLa cells. And these are the ones that we're looking at. And then what is our experiment? What we're trying to do? Well, we're trying to see the biology of the cell by looking at different parts of the cell. One of them is looking at the nuclear envelope. So you may remember your elementary school or high school lessons on biology. We're trying to look at the nuclear envelope. And we're also trying to look at the plasma membrane of the cells. And then if these change in some way, and then we can apply a chemotherapy, then we can understand something of the nature of these cells. Now, how do we do this? How do we do? Well, we have 3 ways. So one of them is what has been mentioned several times, is human manual delineation, someone going and drawing them, then designing algorithms, and then using AI in this process. So I'll mention these 3 options that we have. So the basic one, it comes from the cells that we're going to be acquiring. So how do we get this data? How do we acquire this data? Well, this is acquired in the Francis Crick Institute, which is one of where my collaborators are based. And they use a scanning electron microscope. So they scan one part of the cell, then they slice it. So this is a destructive technique in which they go destroying the sample slice by slice. And then by doing this, they acquire this 3-dimensional set. So the cells may look like they're moving, but in reality, we're going down the sample. So this will be one cell over here, and that's another cell, and that's another cell. And then we have to find for each of those cells, for each of those lines, the nuclear envelope and the plasma membrane. So we take one sample like these ones, and then we can select one cell, and then we zoom into that cell, and then we will draw the nuclear envelope, which is highlighted here in green. and then we do it manually like that. So that's one of my colleagues going one by one of the slides. And here we have an illustration of the mayor of London, Sadiq Khan, that had a go at one of these cells as well. So you do this, and of course, this is very time consuming, it's error prone, and it takes a lot of time. So imagine repeating this for every cell and for every slice, it takes a lot of time. So that is the first option, and there are many people still doing this, and they can do it like that. And now I'm a kind of lazy person. I prefer to code for a couple of hours instead of having to go many hours doing this by hand. So this is how we would do it with HI, and HI is my equivalent of human intelligence. So not everyone is AI, artificial intelligence. This is human intelligence. So applying our knowledge of image processing and computer vision, we can zoom into the cell. Then we apply what is commonly known as a low pass filter to remove grainy noise. Then once we have done that, we're going to look for edge detection. So wherever there is a change of intensity, and we look for those changes of intensity. So this will be a bright part, this will be a dark part. So we detect edges over there. Once we have the edges detected, we will look for the areas that are not covered by the edges. So everything that is outside an edge, and we call that superpixel. So that will be one superpixel, another superpixel, another superpixel there. And then we start applying rules that we call morphological operators. And then we say, okay, let's keep only the large superpixels. So we remove everything that is small. And here you can see we're trying to go for the central one. And then we apply more rules, and let's say, let's discard everything that is touching the borders, and let's keep everything that is not touching the borders. We're nearly there. So let's keep the central superpixel. And there we go. We're nearly finished. We just have to fill in these little holes, but then we can finally have detected the nuclear envelope. And it's not perfect. There are some things that we wouldn't be able to do if we only look at one of these slides, but you should remember that this is a 3-dimensional data set. So if we then think as humans think of going up and down these slides, then we can recover and then find how to do this in 3 dimensions. And this is what we get. How good is this? Well, it's always good to check how good this is. So we can do one manual, one automatic, and then we use several measures of similarity. One of them is called Jacquard, the other one is called accuracy. And before that, we should always compare. I am a great believer that we should always compare our method against other methods. And this is a manual method, not manually drawn, but manually designed. So it's traditional computer vision. So let's compare with AI, and there are many, many architectures as has been mentioned before. So we compared against a different set of AI architectures, and our results came like this. So numerically, how do they look? And these are the accuracy and the Jacquard index of our image processing algorithm against DGG16, ResNet, and insertion ResNet. UNet is not yet here. So we can see that our algorithm outperformed all the AI cases in here. Now, UNet is a very interesting case because UNet had very good results in some parts, but really bad results in other parts. So this is the slices of the cell. So that's the center, and that will be the top, and that will be the bottom. So why is going on there? Well, we checked, and we realized that at the center, where there's only one cell, things were going very well. But as we were going down and up, there were other cells, and UNet was not only detecting one cell, but other cells. So it's not exactly a like with like comparison, and it's unfair on UNet. So what we did is we changed now the ground truth, and we decided to go for more than one cell, and this will be the original one. And then we had more cells, UNet did much better. In some cases, UNet was slightly below the algorithm. In some cases, UNet was slightly above the algorithm. So they were very, very close by. But again, this is not like with like, because UNet is segmenting many cells, and our algorithm was segmenting just one cell. Okay, so we decided to take those results and extend it from one cell to different cells. So those are just some cells in the center. And this is our algorithm against UNet in a certain number of patches that we had 35,000 patches, and then we improved to 135,000 patches. And then we can see that for some things, UNet is very good. And for some things, our algorithm is very good. For instance, this cell, our algorithm did better than in UNet. So we're comparable into these ones. Now we go to the next part, that it was just going for the plasma membrane. and I'll go quickly. So it's not just going for the central part of the cell, but detecting all the cell around. And this is really difficult, even for a human, deciding if this part belongs to this cell or that part belongs to that cell. And we can see that it's taking a conservative decision and saying, okay, the cell finishes here instead of saying it finishes there. But still, we were able to get good segmentation. And if we go then to all the cells, remember this is a three-dimensional, we have many cells, we discard some of the cells that are not quite at the center of the volumes that we take, and we can take all these cells. So with this algorithm, we're able to segment nucleus, nuclear envelope, and plasma membrane, and look at the details, how all these little wiggly things go inside a nucleus. So it's a very, very complex shape. Some of them are easy, some of them are really complex. And this is the final segmentation of some of the cells. We have here in red the nuclear envelope, and that is the plasma membrane, and they are quite different. So this is a very flat cell compared with this one that has many wiggly things. And here is where biologists will continue the work, in which they will say, this is one type of cell, or this one has been affected by chemotherapy in a different way. And all this work has been published. All the papers are open source. The code is open source as well, and the data is open source, so anyone is free to go and compare with these results. And with that, finally, the acknowledgements, and the main acknowledgements is to Henrietta Lacks, because she donated the cells without her knowledge. And with that, I finish, because I think we're running short on time. So thank you very much. Any questions?
Please don't be shy. Okay, please type your questions for Carlos in the question and answer space.
Okay, I'll better stop sharing so I can see the questions.
These are actually, I think these two ones are from the previous.
These are previous questions, yes.
Mm-hmm. Okay, let's give a couple of seconds so people actually have the time to type physically their questions. And I think that Carlos actually has finished, earlier. Okay, you had a couple of more minutes.
Yes, I went quickly to allow some time for the questions.
Yeah. Okay. Okay, Tamila.
How long it takes to run the algorithm? That's a very good question. So manually to segment one slice, because this is a large slice of 2000 by 2000 of one cell, it can take you, let's say, a minute, 2 minutes. Doing one whole cell can take you good part of a working week. That is a manual working part. Of course, it's very precise and people can do it very well. The algorithm, the computer vision program, took some time to develop, but once you have it, it takes about 8 seconds to run one slice. So you can compare from hours to 1 second. Now, training a computer, an AI system, if you have the ground truth and everything, it takes a long time to train, and depends on the settings, as they were mentioning, if you have CPUs or GPUs. And then when you run it, once you want to do the segmentation, it takes again seconds. So it takes about seconds to do one slice of a 2000 by 2000 image. If you run about 300 slices, that is what it takes. Well, it's a couple of 10 seconds, say, for 300. It's a couple of minutes. Still much, much faster than doing anything manual. Are you using trials like segmentation from adjacent cells, like the method of, yes, so we're using knowledge. So if you're a human and you want to make a decision on something and you're not sure, then you go up and down on your slides, and then you compare what is going up and down. We did exactly the same to make a decision. So I went very quickly through that. But if you're going up, we assume that the central slice is where the cell is better defined. And as you go up, it gets smaller and smaller, and it's a bit more difficult to decide. So we took the central slice and we went up, and then we took the central slice and we went down. And then we were comparing the segmentation of one slice with the next one, and then one slice with the next one, and then one slice with the next one. And that's while we were doing decisions, because the cells are not like perfectly round, so they can have like notches that go up on one side. And if you assume that there is only one region, then you will be discarding part of the cell. But if you know that there is a certain segmentation and you trust that segmentation, then you can pass that knowledge to the following cell. So yes, we took that knowledge of cells up and down. And that is like the priors that we were taking into account. There's another question. Thank you to all the speakers. Okay, that is not an actual question. Is there a GitHub source that we can look at the code? Yes, all our code is in GitHub. I can quickly share my last slide. Oh, I need to share the slides first. Share screen. So that is my last slide, and the GitHub code will be Reyes Aldasoro. That is my account, and then it's for HeLa cells. So I have a couple of repositories there, but you can go and check the code there. So all the code is open source. All the papers are open source. All the data is open source, so you can check the data. You can download the data yourself, and then feel free to develop a new algorithm and then publish and see which one gets a better result. So that is how science advances. We compare our results, and then better algorithms go being developed all the time. Could this perform even better by taking perpendicular slices? That's a brilliant question. And yes, if we take perpendicular slices, we can do something better. We haven't published that, but if we take only the horizontal slices, as we go getting higher up, we have a less resolution of what we have. So there will be smaller parts. And if we do it like this and like that, like in traditional CT scans, that we can have axial, coronal, and sagittal, although we don't have that reference here because cells are not humans. But yes, if we take those ones, we can get better results. We have programmed that, we haven't published that, but some of my colleagues have done this in this type of cells, and they call it the three-axial approach, in which you don't only take one axis, but you take several axes, and then you can improve by taking a decision on, let's say we do it in 3 dimensions, and then we take a decision based on the majority voting on the slides. So yes, of course.
Emil, again, one last question, I think.
Okay, is the data set different slides for one cell or for many cells? The original data is 8,000 by 8,000 by 500 slices. And then you will have about 40 cells in this data set. So we start with one cell that is just a region of interest of 2,000 by 2,000 from 8,000 by 8,000 cells. So it's a very, very large data set.
Okay, thank you very much. I think that we have just 1 minute or so, okay, first to thank, obviously the participants and, the speakers, and obviously Stefan. Stefan, you want to mention something before we close the session?
Yes, I'd like to thank you, Eduardo, and all the speakers. It's been a very, very interesting seminar today, and I hope it's been enjoyed by everybody across the board. We have the second seminar coming up on the 14th of July, again at 11 o'clock. This is Technological Innovations in Optometry. And on the 28th of September, we have a seminar, Acceptability, Feasibility and Outcomes in Digital Technological Interventions. And this is looking at some mental health issues. Both of these are in conjunction with the School of Healthcare Science. So I thank everybody for coming along and listening to this fascinating seminar today. And thanks again to all the speakers.
Thank you very much, Stephen. So I think that, we're pretty much, I think it has been just exactly 1 hour since we started really with the talk. So we're on time. So again, thank you very much, everybody. And hopefully see you soon. And as usual, if you actually have any other questions for any of the participants, please contact them directly. Or if you don't know their emails, you can contact Stephen or myself, and we will put you in contact with them. Okay, thank you very much.
Thanks everybody. Thanks a lot.
Thank you. Bye-bye.
Thanks, Aaron.
Bye.
Thank you. Bye-bye.